Good morning, everyone. Let us introduce myself. My name is Ram Seda from Telangana. I have done the topic about filtered matrix. Let us know about what is a matrix. In mathematics, a matrix is a rectangular array or table of number, symbols, or expressions arranged in a row and column, which is used to represent a mathematical object or a property of such an object. For example, is a matrix with 2 rows and 3 columns. Matrices represents linear maps and allows explicit computations in linear algebra. Therefore, the study of matrices is a large part of linear algebra, and most properties and operations of abstract linear algebra can be expressed in terms of matrices. For example, matrices multiplication represents composition of linear maps. In this filtered matrix, there is 7 subtopics. Topic number 1 is introduction, 2 is matrix filter representations, 3 is general casual linear filter matrix, 4 is general LTI filter matrix, 5 is cyclic convolution matrix, sixth one is inverse filter, and the last is the conclusion. Let us know about the introduction. It is numerating to look at the matrix representation of digital filters. Every linear digital filter can be expressed as constant matrix multiply the input signals to produce the output signals vector. It is expressed as y is equal to hx. For simplicity, we will restrict attention's finite length input and the output signal will also be length. Thus, the filter matrix is a square matrix and the input and output signals vectors are column vectors. More generally, any finite order linear operators can be expressed as a multi-matrix multiply. For example, the discrete Fourier transform DFT can be represented by DFT matrix e power minus j2 pi kn by n, where the column index n and row index k ranges from 0 to n minus 1. Even infinite order linear operators are often thought of as matrices having infinite extent. In summary, if a digital filter is linear, it can be represented by a matrix. Matrix filter representations. In this appendix introduce various matrices representations from digital filter, including the important state space formulation. Additionally, elementary system identification based on matrix descriptions is described. To be casual, the filter output at a time n belongs to 0, n minus 1 cannot depend on the input at any types m greater than m. This implies that a casual filter matrix must be lower triangular. That is, must have zeros above the main diagonal. Thus, a casual linear filter matrix H will have entire that satisfy Hmn is equal to 0 for n greater than m. For example, the general 3 into 3 casual linear digital filter matrix operating on 3 simple sequences is H is equal to H00, H00, H10, H11, 0, H20, H21, H22. And the output and input output relationship is of course and more Explicitly, yo is equal to h00xo, y1 is equal to h10xo plus h11x1, y2 is equal to h20x0 plus h21x1 plus h22x2. While equation F2 covers the general case of linear causal digital filter operating on the space of three simple sequences, it includes time varying filter in general. For example, the gain of the current input sample change over its time as h00, h11, h22. General LTI filter matrix. The general linear time invariant LTI matrix is topolized. The topolized matrix is constant along all its diagonals. For example, the general 3 into 3 LTI matrix is given by an restricting to causal LTI filter yields. H is equal to H0, H minus 1, H minus 2, H1, H0, H minus 1, H2, H1, H0. H is equal to H0, 0, 0, H1, H0, 0, H2, H1, H0. Please note, we can handle only length 3 FIRs filter in this representation and that the output signals is cut off at time n is equal to 3. The cutoff time is a sample after the filter is fully engaged by the input signals even if the input signals is 0 at the time n is equal to 3 and the beyond. The filter should be allowed to ring for another two samples. We can accommodate this by appending two zeros into input and going with 5 into 5 Babbittized filter matrix. Let us discuss about cyclic convolution matrix. An infinite topologized matrix implemented in principle a cyclic convolution. The convolutions of a signals x and the impulse response h, in which in both x and h are more than 100 or so sample long. It is typically implemented fasted using FFT convolution. The FFT computers cyclic convolution and unless sufficient zero padding is used. The representation of cyclic convolution is a circulant matrix. Here is example H is equal to H 0 0 0 0 H2 H1 H1 0 0 0 0 H2 H2 H1 H0 0 0 0 0 H2 H1 H0 0 0 0 0 H2 H1 H0 0 0 0 0 H2 H1 H0. As in this example, each row of the circulant matrix is obtained from the previous by a circulant right shift circulant matrix. They are always topolized. Circulant matrix have many interested problems. For example, the eigenvectors of n into n circulant matrix are the DFT sinusoids for the length n DFT. The eigenvalues are found by simple taking of first row. The DFT structure of circulant matrices is directly related to DFT convolution theorem. The above 6 into 6 circulant matrix H when multiplied times a length 6 vectors x implemented cyclic convolution of x with h is equal to h0 h1 h3 0 0 0 using the DFT to the perform the circular convolution can express as u is equal to x into h is equal to IDFT into DFT x DFT h, where star denotes circulant convolution. Let's denote the matrix of sample DFT sinusoids for the length and DFT. Then A star is the DFT matrix. Let us talk about inverse filters. Note that the filter matrix H is often invertible. In this case, effectively runs the filter backwards. X is equal to H inverse H power minus 1 into Y. However, an invertible filter matrix does not necessarily correspondent to a stable inverse matrix when the length of the input and output vectors are allowed to grow larger. For example, the inverted filter matrix may contain truncated growing exponential as illustrated in the following MATLAB example. Greater than h is equal to topologize bracket 1 comma 2 comma 0 comma 0 comma 0 into 1 comma 0 comma 0 comma 0 comma 0. H is equal to 1 0 0 0 0 2 1 0 0 0 0 2 1 0 0 0 0 2 1 0 0 0 0 2 1. Inverse V answer is equal to 1 0 0 0 minus 2 1 0 0 0 4 minus 2 1 0 0 0 minus 8 4 minus 2 1 0 16 minus 8 4 minus 2 1. The inverse of the FIR filter H is equal to P. 1 comma 2 is in the fact unstable having impulse response. Another point of note is that inverse of the bonded topologized matrix is not banded. Although the inverse of lower triangular matrix remains lower triangular, this corresponding to the fact that the inverse of the FIR filter is an IRR filter. The conclusion: the model does not need any data about other users since the recommendations are specifically to this user. This makes it easier to scale to a larger number of users. The model can be captured the specific interest of a user and recommended a needed item that very few other users are interested in. Thank you.